sample means. And we look to say, well, what's the likelihood that the true population mean fits inside that interval? We're not saying how close the population mean was to the sample mean, but if you look, you start with sample 1, it was in there. Sample 2, it was in there. Sample 3, it was in there. Sample 4, a little bit higher IQ for whatever reason on that sample. The true population mean wouldn't have been in there. Sample 5. So what you're looking for is intervals. And look how often the point estimates, there's only really sample 3 was the one that came really close. So you determine these intervals with the hope that you've got a better idea or an interval estimate for your population parameter. In this case, the parameter was mu. Okay, so difference between what we're doing in the previous sections, in the previous recording session, we looked at sampling distributions, particularly went and looked at one for sample mean. And remember that this is the probability distribution associated with sample means. So I draw samples out of so I have a population, normal distribution, maybe we'll go back to the salary example, and then I keep drawing samples. And for each sample, I note down, okay, what was the average salary? Mark it down. Draw another sample a different time and mark down the sample mean on that one. What was the average salary? And do that over and over and over. I come up with a probability distribution function associated with the sample means, and we call that a sampling distribution. Well, what we looked at in there was we were talking about what is the probability that a sample will have a mean greater than some value given the population mean mu is known. And so the middle, what you're showing, probability, this was actually, I think, one of the exercises we did, or I did during the recording session. What's the probability that the sample mean was greater than 85 given the true population mean was 75? And we determined that was a 0.0668, that a sample mean would be greater than 85 given the true population. So a little bit kind of funny to have said, oh yeah, we would have known the population mean, the true population mean. So if you did, then why'd you go do a study about sample means? Now we're going to peel that back. Okay, we're going to relax that and say that we understand that we don't know the true population mean. And we're going to work with our sample information, our sample mean value. What's the probability? So now we assume that we don't know the true population mean. We ask the question, what's the probability that the true population mean, mu, falls in an interval that's around the sample mean? Okay, so confidence interval, formal statement. If a random statement, x1 through xn, arises from a normal distribution and mu is unknown, we use the sampling distribution, x bar, sample mean, to construct a confidence interval for mu. That is where my last recording session, when I talked about sampling distributions and the central limit theorem and how broad that is and the importance of it, this is where we start to see that. Namely, we can find a z-value for alpha over 2 such that the probability that, again, you have a sample mean, and what we were working with was a known mu. So now we're going to construct an interval around the sample mean, understanding that we don't know what the population mean is. So we're going to find the probability 1 minus alpha such that we would hope that the sample mean is just so many standard deviations away from the true population mean. So basically you can do some algebra with the first equation you see there, and you end up and say, okay, alternatively, we can say that with 100 times 1 minus alpha percent confidence that the true population mean will fall somewhere in the interval x minus the z of alpha over 2 times sigma, which is the standard deviation of the underlying population, divided by the square root of n. Remember that standard deviation, sigma divided by the square root of n, was the standard deviation for the sample mean sampling distribution. So that's the lower side. You take off a number of standard deviations, and on the right side, you're going to add it. So you've got this interval now, as you see on the lower equation there. Observations about the impact of n. So just intuitively, as the larger sample sizes you take, the larger the amount of information you have. So again, we say with 100 times 1 minus alpha % confidence that the true population mean will fall somewhere in the interval. This is the same thing as I had on the previous slide. If you look at this, as n increases, then what's happening is on the bottom part of that, n is getting bigger, so therefore the size, the variance in your sampling distribution is shrinking, and you would have what I call the width, the resulting interval would be a lot smaller because that factor, that sigma over the square root of n, is getting smaller as n gets larger. So with the same amount of confidence, that 100 times 1 minus alpha %, you're getting a tighter and tighter interval to work with. And if you can afford to get larger sample sizes, if you have the time if you have the time or the money, the resources to get larger sample sizes, you'll try and do that. Shorter confidence interval indicates more reliance on sample mean as an estimate of the population mean. Statisticians not restricted by time, money, and effort or availability of items can make the interval as tight as they want, as short as they want, as they like by increasing the sample size n. Okay, learning checkpoint. Give a shot at this, and again, you're going to be working with, you're going to create a confidence interval using this bottom equation here. You take your sample mean, you decide what level of confidence you want, and so you have your sample mean, and you're going to be working to create a confidence interval as defined here. Suppose it is known that the distribution of salaries of a certain group of people has a standard deviation about $2,000. To make a statistical inference about an unknown mean mu, a random sample of size 16 is taken, and the resulting sample mean is found to be 23,412. What is an approximate 95% confidence interval for mu? What would this interval look like if instead of 16 you had 100 observations? What is an approximate 99% confidence interval for mu? Okay, so if 95% confidence, and what we were talking about with alpha then, how does that relate? 95% confidence is 100%, 100 times 1 minus alpha. So alpha, therefore, must be 0.05. And the z that you're looking for, then, is 0.05 divided by 2, or 0.025. So z of 0.025, that would be leaving 0.025 in the tail of a normal distribution on either side of the tail. And so that gets you your z values. So first we're looking for, we use the sample information. We've got a standard deviation for the true population, We have a sample size n of 16. We have sample mean, 23,412. And now we have the z of alpha over 2, which is alpha z of 0.025 in the tails. You can construct first a confidence interval for that. You can then modify it and make n equal to 100, see the impact of that. And then further, you go and you check out, okay, what if I want more confidence? And think to yourself, would that make a bigger confidence, wider confidence interval, or a shorter one? Okay, so go give that a try. As usual, the solutions are out on the blackboard. I've also got a couple of textbook exercises that you can give a shot at. Additionally, ask the question of what is the confidence interval for mu when both mu and sigma, the standard deviation of the underlying distribution, are known and n is small. Let me ask that question again. What is the confidence interval for mu when both mu, the true population mean, and the standard deviation for the population are not known, and you draw small sample sizes? Remember what we did with the n less than 30 when the standard deviation was not known. And in the previous recording session, I was introducing what is a t-distribution and how did that tie into this. Okay, so there's some additional textbook exercises related to that as well. Okay, so I'm going to wrap this up. This is a brief glance into estimation. In this case, I looked at it from the standpoint of one sample mean being used as an estimator for a true population mean. As you go through your chapter 9 of your textbook, you would see a number of other estimation topics developed, and I'll leave it to you to go look into those as well. And that concludes this recording session.